Okay, OChem 1 students, we just learned about arrow pushing and we are applying it here in the context of Lewis acids and bases, which, as a reminder, Lewis acids and base is a category that includes all Bronsted-Lowry acids and bases. This is like rectangles and squares. All Bronsted-Lowry acids and bases are Lewis acids and bases, but not all Lewis acids and bases are Bronsted-Lowry acids and bases. We saw in our first example some Bronsted-Lowry acids and bases. An electron donor, oxygen, bonds to a hydrogen, and an OH bond is given back to an oxygen. This reminds us of two things. When a bond breaks, it breaks toward the more electronegative atom. When the OH bond breaks, those two electrons go between one of the two atoms, and it's always the more electronegative of the two. When a bond forms, it forms from the more electronegative atom. When this new OH bond forms, it is the electrons of oxygen that are used to create the bond. So we see in our products a new OH bond and a broken OH bond. And we understood that the electrons that created O- came from the OH bond back to the oxygen, and the electrons that created the new OH bond came from the oxygen. We see this again with a new Bronsted-Lowry acid base, again also Lewis acid base, this being my electrophile, also my acid, this being my nucleophile, also my base. A bond forms between O and H because of the electrons from O. A bond from C and H breaks back to the carbon, which in turn creates this new carbon-carbon bond. So here we have some examples of reaction steps that make and break bonds without any arrows. Based on the bonds that form and break, we'll decide what arrows are needed. And here we have arrows shown in reaction steps, and based on those arrows, we'll decide what the products should look like. So in some analysis in this first problem, top left, a carbon-carbon pi bond breaks. MO theory tells us pi bonds are the highest energy and the most likely to break. So it makes sense that the sigma bond is preserved. The pi bond breaks. Also breaks an HBr bond. What we don't see explicitly is that a CH becomes a CH, and a CH2, a CH becomes a CH plus, and a CH becomes a CH2. So what we see also is that a bond forms between carbon and hydrogen. So two bonds break. Carbon-carbon bond breaks, hydrogen-bromine bond breaks. One bond forms. A carbon to hydrogen bond is created. When a bond breaks, let's take HBr, it breaks to the more electronegative atom. That means that these electrons are taken by the bromine. This is how we create Br minus. When the carbon-carbon bond breaks, and we say it breaks towards the more electronegative atom, well, there is no more electronegative atom, they're the same. So either carbon here has a chance of using it. It just turns out that one of them uses it. So carbon-carbon bond attacks the hydrogen. These two electrons no longer make a pi bond. They're now used to make a carbon-hydrogen bond. Let's do one where we see the arrows. We see one bond forming. A carbon attacks a carbon. This means that in my product, I should see a new carbon-carbon bond. This also goes against our rules. Bonds form from a more electronegative atom. Carbon is not more electronegative than carbon. But this carbon here, with a true negative charge, is attacking a carbon here with a partial positive charge. And that's a partial positive carbon because of its bond to oxygen taking electron density towards itself. So a new bond forms, carbon to carbon, and we see that. A bond also breaks. The carbon-oxygen double bond breaks. If I had two bonds and one bond is breaking, now I only have one bond. If I had two lone pairs on oxygen and now a new bond is coming to create a third lone pair, I now have three lone pairs. Three lone pairs on an oxygen with one bond gives us the negative charge. Let's do it again. Pause if you haven't already so you can attempt these problems down here. We analyze what bonds form and what bonds break. I need to break a carbon-chlorine bond. I need to form a carbon-oxygen bond. Carbon to chlorine, chlorine is more electronegative. Oxygen and carbon, oxygen is more electronegative. The carbon-chlorine bond breaks to the chlorine, the more electronegative, and the oxygen donates electrons to attack the carbon. In both of these cases, we have our nucleophile attacking and our electrophile being attacked. We did this one in class. We said that we saw a bond forming between oxygen and boron. Because this was net neutral, I need to also have a net neutral product, but oxygen with 3 bonds takes on a positive charge. Boron with 4 bonds takes on a negative charge, net neutral. In both of these examples, our nucleophile attacked and our electrophile was attacked. I'm using abbreviations here for nucleophile and electrophile, just so we don't have to spell it all the way out. Now this one is our most challenging reaction, in part because not every bond that's needed is explicitly shown. So we need to interpret some of our bond line structure in order to make sense of what's happening and add arrows. First, oxygen with a negative charge becomes oxygen bonded to H. So I need to form a bond between O and H. I have a carbon and a carbon bonded to each other, single, and now I have a carbon and carbon double bonded to each other. So I need to form a carbon-carbon double bond. This one is going to test our rule. A bond forms from a more electronegative atom. If I'm bonding carbon and carbon, neither will be more electronegative. So I will need to use context of what other bonds are happening to make sense of this. I need to break a carbon-hydrogen bond. I have a CH2 that becomes a CH. I need to break that bond. I also need to break a carbon-bromine bond. I have a CHBr that becomes CH, and I need to break that CBr bond. There's no right way to start this. However, I'm going to start by taking the structure I had down below. I think I will redraw this since I have kind of drawn over it. And I'm going to explicitly highlight one of those carbon-hydrogen bonds because I need to break it, meaning I need to have it shown. While I break this, I know that carbon will get it back, and I also know that oxygen will need to donate electrons to form the bond to that hydrogen. So this negative charge represents electrons. I don't need to show the lone pairs if I have that negative charge. Now, I know these electrons will go back to carbon, but I'm not quite sure how carbon will use them. So let me now show that the carbon-bromine bond breaks. That, of course, will break towards the bromine because bromine is more electronegative. The only thing that I have not done yet, I have not broken the carbon-hydrogen bond, and I have not formed the carbon-carbon bond. That tells me that the carbon-hydrogen bond that breaks will be used in forming the carbon-carbon double bond. So I'll take these 2 electrons, and I'll move them from the carbon-hydrogen to the carbon-carbon double bond. This is very similar to what we saw up above when we formed a carbon-carbon bond. I form CH3OH. I form CC double bond. The only thing that this reaction didn't tell me to expect was the bromide ion. And checking for conservation of charge, this entire reactant side had a -1 charge. And now this entire product side has a -1 charge. So I'm set on my charges. My arrows all agree with the bonds that need to break and the bonds that need to form. And the direction of those arrows follows electronegativity rules. Okay, keep practicing. Happy studying.